I'm Simona. I'm a first-year PhD student at the University of Birmingham, working with Clement. And today I'm going to talk about magnetic fields in TDEs. Let's see if this works. No. Okay, so why magnetic fields? There are many ways in which magnetic fields can affect the dynamics of TDEs and potentially affect the signatures in observed light emission. And this is because common stars have magnetic fields, and when they happen to be disrupted by a massive black hole, then their magnetic field gets transferred to the debris, and it will participate in the subsequent evolution. And there are many ways in which magnetic fields can be relevant. For example, at early times, in the case of partial TDEs, the disruption process can strongly amplify the magnetic field. Instead, during full disruptions, while the stream is coming back to pericenter, the magnetic field can become dynamically important, and the main resulting effect of this is a fast increase in the stream thickness. And in the unbound part of the debris, this increase in the width can change the way the gas interacts with the ambient medium. And as we already heard, this can affect radio emission signatures. And if we go back to the evolution of the bound debris, later on, after pericenter passage, this is expected to self-intersect, and the increase in the width can change the strength and the outcome of the shock. And ultimately, it will affect the formation of the accretion disk. And in these last stages of the TDE, magnetic fields play a crucial role. And this is because regardless of the dynamical impact of the magnetic field at earlier times, here magnetic fields will probably provide the viscosity that is needed in order to power accretion through the magnetorotational instability. And there are other implications, as we heard in previous talks, and I will be happy to discuss this during the conference. But today, I will focus on the early evolution of magnetic fields, since this is the first step in order to understand the later evolution of the TDE. And there were already some works done in order to understand this phase of the evolution. However, as I will show in this talk, with my work, I was able to follow the stream long enough to see the effects of the dynamical impact of magnetic fields. So to study this problem, I used the code Gizmo to run an ideal MHD simulation of a full disruption of a solar mass star by a massive black hole of 10 to the 6 solar masses. And the star is initially modeled as a polytropic sphere and is placed on a parabolic orbit with impact parameter 1. And the image that you see is the initial condition, and the arrows represent the initial direction of the magnetic field. And we set the magnetic field initially to be straight and homogeneous throughout the star. And we are aware that this is a very simplified assumption, and it's not realistic, and I will comment later on how a different initial configuration can affect the results. And in terms of magnetic field strength, we consider a range of values, and we always make sure that the magnetic field is not dynamically important at the beginning of the simulation. And as you can see, we also consider some very strong magnetic fields, and the reason why we do this is mainly for computational convenience. In fact, as I will show soon, it is computationally unfeasible to see the dynamical impact of the magnetic field if you don't have an initially very strong magnetic field in the simulation. And unfortunately, we don't have many constraints about magnetic field strength in main sequence stars, which could support this choice. But we have some asteroseismology studies which found these strengths in the cores of red giants. So now I'm going to show you the movie of the simulation in a frame that is co-moving with the center of mass of the star. So let's see. Oh, yeah, it works. So if you focus on the arrows indicating the direction of the magnetic field, you will notice that these are aligning with the direction in which the stream gets elongated. And the reason why this happens is magnetic flux conservation. And now I'm going to explain you with a simplified picture why this is the case. So the stream can be locally approximated to a cylinder whose width and elongation evolve over time. And now imagine that the magnetic field was not aligned, the pink arrow is not aligned with the direction of stretching. Now, because of magnetic flux conservation, both the components of the magnetic field are supposed to evolve in such a way that they are inversely proportional to the area that is perpendicular to the corresponding direction, which is what I'm telling with the pink formula. And we know that over time, this cylinder is going to evolve and it's going to grow. In particular, we expect it to get elongated, and also its width will increase, which means that both the parallel component of the magnetic field to the stretching direction and the transverse component will decrease over time. However, the stream gets elongated much more than its width is increasing, which means that the transverse component of the magnetic field will decrease much faster over time. And this will align the magnetic field to the stretching direction. And the reason why I spend so much time on this is that the alignment of the magnetic field is what allows the magnetic field to become dynamically important. And now I'm going to explain you what I mean when I say that the magnetic field becomes dynamically important. So in gas, magnetic field acts as if there was an additional pressure, and I'm going to call this magnetic pressure from now on. If this magnetic pressure happens to exceed gas pressure, then the magnetic field will start to affect the dynamics. And now I'm going to explain why this is the case in TDEs. So as I said, at some point the magnetic field aligns with the direction of stretching, but this constrains the evolution of the magnetic field. In particular, this will go like 1 over the width square. And here I have a movie that visualizes this. So here I'm showing a section of the stream that is seen in such a way that the direction of elongation is always perpendicular to the screen. And it's in the center, it's in the frame that is co-moving with the center of mass of the section. And the color bar is the magnetic field strength. So as the cell gets disrupted, the stream expands and the magnetic field decreases by orders of magnitude. So now that we know how the magnetic field evolves, we can estimate how the magnetic pressure evolves as a function of the width. And we can do something similar with gas pressure and express it in terms of the width and of the elongation. But now we also know from previous studies how the elongation and the width evolve with the distance from the black hole. And if we plug this in, we will find how magnetic pressure and how gas pressure evolve with the distance from the black hole. And as you can see, gas pressure decreases much faster than magnetic pressure, which means that at some point magnetic pressure will exceed gas pressure and it will start to affect the dynamics. So here I'm showing the evolution of the ratio between gas pressure and magnetic pressure as a function of the distance from the black hole. And the bold line is a case with an initially strong magnetic field. And as you can see, at some point, at around 100 tidal radii, the ratio approaches 1, which means that from that point on, the magnetic field will start to affect the dynamics. And here I'm also showing a case with an initially low magnetic field. And this is to show you that since now the ratio is very big initially, it will take much, much longer for the magnetic field to have an effect on the stream. And this is computationally very expensive. So the relevant case of study for us is the strong magnetic field case. So now, as soon as the magnetic pressure exceeds gas pressure, we expect the stream to expand. This is the main effect that we expect to see. So we measured the width in the simulation. And to do this, I divided the stream in different sections that are featured by different orbital energies. And I computed the width by taking the radius of a circle that contains 50% of the mass in the transverse direction. So now I'm going to show you first a case without magnetic fields for a parabolic stream element. As you can see, the width increases, and it follows this r to the 1/2 scaling, which is the theoretical prediction in the case when the stream element is in hydrostatic equilibrium. But now if we have a magnetic field, now we have that together with gas pressure, there will be another pressure, magnetic pressure, which will work to counteract self-gravity, and the width will start to increase much faster. And because of this fast increase, the magnetic pressure will initially start to drop. So for some short amount of time, the stream will not be affected by any force, and it will expand at constant speed. However, this free expansion phase doesn't last very long. In fact, what we see in the simulation is that as the magnetic force decreases, it approaches the tidal force, and we see that the stream element enters a regime where there is equilibrium between tidal force and magnetic force. And this equilibrium produces this r to the 5/4 scaling in the case of a parabolic stream element, and it changes to an r scaling for the case of an unbound stream element. And this can all be recovered analytically. And finally, in the case of a bound stream element, the magnetic field becomes important while the stream is moving outward. But as it comes back, the tidal force takes over and it dominates the dynamics. So this is the main result of the simulation, and it's quite satisfying since, together with some simple analytic calculations, it gives a quite simple explanation of how magnetic fields evolve in TDEs. However, we know that there are some limitations. In fact, simulations are expensive, and we can consider just a limited amount of initial conditions. So to overcome these limitations, I developed a semi-analytic model, which is based on a model which was introduced by Clement, and which I generalized to include the effect of magnetic fields. And this model consists of dividing the star again in slices of different orbital energies, and to evolve each of these slices starting from pericenter and solving a set of differential equations that approximate the dynamics. So here I'm going to show the comparison of the simulation and the model. So this again is the result of one simulation with an initial magnetic field of 10 megagauss. And the orange line is the result of the model, so the result of obtained by solving the differential equation on the left. And so the two lines behave very similarly. In fact, we can see that they both follow this r to the 5/4 scaling expected when tidal force and magnetic force are in equilibrium. And the reason why this model is convenient is because we now can cover a bigger part of the parameter space, and we can see the impact of also lower magnetic fields. And another reason why this model is convenient is because it allows us to follow bound stream elements. In fact, with the simulation, we can only follow the most bound stream elements. Instead, with the semi-analytic model, we can follow all bound parts of the stream. And here I'm showing an example for different initial magnetic fields. And as you can see, when we include a magnetic field, as the stream is coming back to pericenter, its width is going to be bigger. And the bigger is the initial magnetic field, the bigger the width as the stream is coming to pericenter. And we can use this result because it provides us with the magnetohydrodynamic properties of the stream as it comes back to pericenter. And we can use this to study the later evolution of the TDE. In fact, knowing the hydrodynamics in the outflow and knowing the magneto-hydrodynamic properties of the stream from this work, we can try to predict what is the property of the outflow in the case of magnetic fields. And in particular, we can try to predict what is the magnetic field distribution in the outflow and use that to study the formation of the accretion disk. So in summary, what I did was to run the first simulation that shows the effects of the dynamical impact of magnetic fields on a magnetized tidal stream, and the results agree both with analytic calculations and with my semi-analytic model. And the semi-analytic model provides the magneto-hydrodynamic properties of the stream as this comes back to pericenter, and this can be used to study the later phases of the TDE. So there are some limitations, as I mentioned at the beginning. We considered a very simplified initial magnetic field configuration, and if we change the geometry of the magnetic field, we don't expect to see a change in the dynamical impact of the magnetic field, but we expect this to change the later phases of the evolution. In fact, if we had, for example, initially a toroidal magnetic field, this would change the magnetic field configuration at the self-crossing shock, and this would also affect the outflow and therefore the accretion disk and perhaps the development of the MRI. Something else that we didn't include is recombination, which is something that becomes important as the stream expands and cools down. And as the gas recombines, some additional energy can be injected in the stream, and we expect this to have a similar effect to that of the dynamical impact of magnetic fields. So we expect to have a further expansion of the stream. And as the gas recombines, the ideal MHD assumption breaks down, so also non-ideal MHD effects should be taken into account. And finally, something we would like to do is to use everything we learned from this work, from the simulation, the semi-analytic model, to initialize an MHD simulation of a TDE accretion disk. And I'll stop here and take questions.
Any questions? Hi, really great work. I have a couple of questions actually. So firstly, I guess you did a simulation of a full tidal disruption. How would you expect things to change if it was a partial tidal disruption? Would magnetic fields even affect how much mass is lost from the star? And secondly, you used a polytropic model of, I guess, five stars you said?
Yeah.
If you use a realistic stellar model or let's say another polytropic model, would you expect the semi-analytical model you use to work as well? I guess with different power law relations, of course.
Mm-hmm. So first question was about partial TDEs. So there was actually some work done on magnetized partial TDEs. And as I said, the main effect is to increase to amplify the magnetic field. And so I think there are people who know more about this. So one of the effects of having a stronger magnetic field could be to, for example, it could affect the evolution of the unbound part of the stream. In fact, the unbound part of the stream can interact with the ambient medium. And if you have a magnetic field, this can help to suppress like the instabilities that develop when the gas interacts.
So you could have different amount of mass lost from the star?
I honestly don't know. And the second question?
The stellar model itself, how would it change your results?
Yes, so I guess the way it would change, so the main point is that to see the dynamical impact really depends on the initial condition. So how big is the ratio between gas pressure and magnetic pressure at the beginning of the simulation? And if you change the stellar model such that the star is more centrally concentrated, for example, then you expect to have a dynamical impact much later.
Sure,
and
yeah.
the opposite.
Thanks.
It was, yeah.
So I have a question related to the disruption process itself. So during the disruption, you have lots of shear motion. Is it possible, maybe you already see that in your simulation, do you find any amplification of the B field? Let's say if you start from 1 million Gauss, does it get larger than that during the disruption?
No, it only decreases in the simulation. The magnetic field.
I mean, during the compression of the disruption near the first pericenter passage. Mm-hmm. And then you can imagine there's a lot of shear going on. So, but in your simulation, you don't see any amplification of B fields.
No, I don't see any amplification.
Is that because your initial magnetic field is aligned with the stream, mostly? Because if you have shear like in the direction of motion, then that would amplify the magnetic field, I think. If you have some magnetic field that is perpendicular to the
Sorry, I can't hear you well.
Yeah, so if you initialize the magnetic field in the direction of the stream, then you don't have a lot of magnetic field in the perpendicular direction. In that case, you may not be able to find shear amplify the magnetic field. I'm not sure.
So what would cause the magnetic field to increase is a compression, right?
No, I'm asking like, have you initialized the direction of your magnetic field in the direction of the stream or the?
It's in the orbital plane.
Orbital plane is two directions, right? What is the?
Yeah, it has components both in the X and Y direction.
So you don't have.
There is, of course.
Do you have magnetic field that is perpendicular to the direction of the shear?
Yeah, so I guess it's like if you think about like the direction of pericenter, for example, right?
Yeah.
Is like that the original direction of your magnetic
field? Yeah,
field?
there is some initial component along that direction.
Okay.
Yeah, there has to be some, otherwise we won't see the dynamical impact. So the main point is that in order to have the dynamical impact, the star has to have initially some magnetic field in the direction in which it's going to be elongated. And this is very likely since the star will be launched randomly on the black hole.
So I guess it's possible that if you have some other magnetic field that is perpendicular to that direction, it could get amplified by the shear and that could actually become very large. Maybe, I don't know.
I honestly don't know, I'm sorry.
We can talk about this.
Yeah, I would like to.
Very interesting work. So can you possibly infer the presence of these fields from observational signatures, like kind of light curves, or I don't know, anything like that?
So I haven't done work related to this, so I'm not sure. Yeah, I'm sorry, but we can talk about this.
And last question is just out of curiosity. If the black hole has also magnetic fields like spinning, that will be a very, I guess, complicated picture with the accretion disk also having magnetic fields. So have you thought about exploring things like that?
Yes, so during the last phase of the TD, when you have the accretion disk, the magnetic field, as I mentioned, it's going to be important because it can allow gas to be accreted. So
I was wondering if the black hole is initially spinning.
If the black hole is spinning.
Yes.
So I haven't studied.
Okay.
I just studied the early evolution of the TD, where the spin is not important.
Okay, thank you.
You're welcome.
I actually have a quick question related to the observational signatures. So in these jetted TDEs, as we were describing earlier, some of them show this abrupt shutoff. And so if the supply of the magnetic field to the black hole has anything to do with what's powering it, could it be that once the magnetic pressure comes into rough equipartition with the gas pressure, you puff the stream up and KH like destabilize it and basically destroy the stream and therefore shut off the magnetic field supply to the black hole? Sorry, Kelvin-Helmholtz sensibility. Sorry, yeah, the Kelvin, like basically you drop the gas density more rapidly and you destabilize the stream and you shut off the supply of the magnetic field to the black hole.
Yeah, I don't know. I'm sorry. Okay. I haven't looked into this. I'm sorry.
That was great. Thank you. So just to connect to Clement's talk, so you ended up with a slightly thicker stream in some configurations. So when that goes through the nozzle shock and does the subsequent dynamics, will that be more dissipative and potentially radiatively brighter? I mean, is this effectively another way of puffing up the nozzle shock and increasing the efficiency of circularization?
Yes, so at this crossing shock, so we expect to have a stream that is wider. This means that it's going to be less dense, and it might produce a less strong outflow shock. And regarding the nozzle shock, I think it's not clear what would happen when you have magnetic fields. But like if we believe what Clement was presenting, that the stream will be compressed and then rebounced back. In the case with magnetic fields, it might happen the same, but instead of having this rebounds due to gas pressure, it would be due to magnetic pressure.
Thanks.
All right, let's thank Simona again.